Hi everybody, today we're going to be learning about dilations 2.21. You're going to need a ruler and 3 colored pencils or highlighters. Hi everybody, this is Mrs. Martinez. This is just my formal warning. Do not be distracted by all the dogs barking. My dog Peanut is a very adamant barker, as are my neighbor's dogs. My apologies. Enjoy the video. So now I'd like you to go ahead and turn to page 22, where we're going to be talking about triangle dilations. And I want you to remember that a dilation is an enlargement or a reduction. So we're going to start by reading question 1. I'm going to walk you through question 1 together. We're going to do that one together, and then you guys are going to do question 2 on your own. So here's what it says. Given triangle ABC, use point M as the center of dilation. So that seems important. So use point M as the center of dilation. Use that to locate the vertices of a triangle that has the side lengths that are 3 times longer than the sides of triangle ABC. So 3 times longer. Okay. So the first thing that you'll need to do in order to dilate this triangle, and I'm noting that they told me it should be 3 times longer, so I'm guessing my new triangle is going to be much bigger, 3 times bigger. In order for me to do that, the first thing I'll need to do is figure out what the relationship is between the center of dilation and each of these vertices A, B, and C. So the first thing I need you to do is to very carefully draw a straight line from M to A, from M to B, and from M to C. And then you can unpause the video and we'll keep going. So you've gone ahead and you've drawn in your lines for MA, MB, and MC, and your triangle should look something like this. Your next step is actually measure each of those lines. So what you're going to do is you're going to take your ruler and you're going to line it up, let's say from M to A, and you're going to note what the distance is from here to here in millimeters. So in this case, MA would be, remember this is 1 centimeter, so that's 10 millimeters, 15, 16, I'm going to say 17, 18, I'm going to say 18. So once you've found that measurement, you're going to go ahead and grab your pencil, and then you're going to note that that is 18 millimeters. Go ahead and measure all of the sides, and then unpause the video and we'll continue moving. So you've measured all your sides, and hopefully you got something close to what I found. We noted that MA was 18 millimeters, and you should have measured MC. I got 49 millimeters, and MB 56 millimeters. If you're off by 1 millimeter or so, that's fine. More than 2 millimeters, you probably measured wrong. Okay, so now our task is to see what this triangle would look like if it were 3 times its size, using M as the center of dilation. So what we're going to do is we're going to use that scale factor they gave us of K, our scale factor of 3, and we're going to extend these lengths out to make a triangle that is 3 times bigger. So what we're going to note is that if we want to find where this new point B is, because it's going to be 3 times further down this line, or if we're going to note where point A is, which will be 3 times down this line, or C for that matter, we're going to need to do some calculations down here. So what you're going to do is you're going to find that if you want to find where the new point MA is, or MA prime, because point A, this is point A prime is going to be further 3 times down this line, it's going to be equal to whatever the measurement of MA was times whatever the scale factor is. So in this case, MA was 18 millimeters, and our scale factor was 3 because it's 3 times bigger. And I'll go ahead and be your calculator today and tell you that 18 times 3 is 54 millimeters. Well, we're going to do these calculations for all 3 of these lengths. So for MC, or MC prime, because C will be the point that's moved down, that'll be the length of MC times our scale factor again. This time it'll be 49 millimeters times 3. And when we do our math, we get 147 millimeters. Okay, lastly, to find MB prime, we're going to take whatever our distance was of MB, multiply it times our scale factor again. This time we'll do 56 times 3, which is 168 millimeters. So now your task is to take each of these lengths and make them extend out to their new length. So MB, for example, which was originally 56 millimeters, is now going to extend out to the MB prime length of 168 millimeters. So you'll extend this all the way out 168 millimeters. MA prime is going to extend to 54 millimeters. So this MA line is going to continue on longer to 54 millimeters. And lastly, MC, that was at 49 millimeters, is going to go to its new length of 147 millimeters, all the way out here. Now when you do that, what you're going to end up getting, if we scroll over, is something like this. So you're going to extend those three lines and make your new points B prime, A prime, and C prime. Once you've labeled your 3 points, go ahead and unpause the video and we'll continue from there. So now hopefully you've labeled your points A prime, B prime, and C prime, even though we extended a little bit into our question 3. But if you connected your 3 points, you should clearly be able to see that your pre-image, so here's your pre-image, has been tripled into this triangle. This is your image. And now clearly we can see that our pre-image was enlarged to this triangle, this image, and that because our K value was 3, a number bigger than 1, if your dilation scale factor is bigger than 1, your image will be enlarged. Now you've seen me do it, now it's your turn. So here's what you need to do. You're going to use point N now, so N is your new center of dilation, and you're going to be locating the vertices of a triangle that has the side lengths that are 1/2 the length of triangle ABC. So this time, instead of using this M point, you're going to use the N point down here. You're going to have to take your ruler and connect all of these lines, and then you'll have to do some measurements to find those values of each of those sides. Once you've done that, you'll need to find half of those values to find your new vertices, and make sure that all your measurements are in millimeters. When you're ready, unpause the video and we'll take a look at what you've got. So here's what I hope you did. I hope that you first drew those lines to connect all of the vertices to the new center of dilation at point N. I found that my distance from A to N was 108 millimeters. I forgot my millimeters there. And that my distance from B to N was 71 millimeters, and from C to N was 91 millimeters. And then I halved all my values to find my new points here, here, and here. And those were at 54 millimeters away, 35.5 millimeters away, and 45.5 millimeters away. Don't forget that if you're if you're 1 millimeter off in one direction or the other, that's not a huge deal, but if any more than that, you probably measured incorrectly. Now, once you've connected your these 3 vertices together to reveal your new points, this is what your entire diagram should look like. I'd like you to note that I wrote that this point right here was A double prime, B double prime, and C double prime, which actually makes me want to go back here and fix these to A double prime, B double prime, and C double prime. The only reason why I'm changing these values here is to differentiate these points from the ones we made when we enlarged the triangle. We wouldn't want to call them by the same point. Anyway, this is what your final image should look like. And now we're ready to start talking about the relationship between these three triangles that we've created through dilations. So now I asked you to have three different colors available, and I'd like you to highlight each of the three triangles we created. This was our pre-image, and then we have two images that we created through dilations. Triangle A prime, B prime, C prime represents one of our triangles, and triangle A double prime, B double prime, and C double prime represents our other triangle. Go ahead and highlight those, and then we will take a closer look at them. So the first thing I want you to consider is what these triangles really are. So let's actually take these triangles out of this picture. And let's get rid of this guy. And just take a look at what we have here. This is our pre-image, and these were the two images that we created as a result. So now what I'd like you to do is really think about, how do these triangles compare to one another? How does this pre-image compare to our two images? The first thing I want you to take a look at is, what do you think about these angles in here? What do you think happened when we took this triangle and enlarged it by 3 or cut it in half? What happened? Well, let's check. If I take my original triangle and I overlap it with my giant triangle, you can see that the corresponding angles are exactly the same. They're the same in every single vertex. And the same goes for the smaller one. It's harder to see. And this one I need to rotate a little bit, but believe me, all of the angles overlap exactly. What does that mean? What can we deduce from that? Well, so let's record that information. So one of our observations that we just made, is the following. We said, okay, the angles are overlapping. That means the corresponding angles are, I'm going to expand this just a little bit, are congruent. Okay, I agree. All right, something else I notice is that even though I took this small figure and enlarged it, or I took this small figure and I reduced it, it's still the same shape. It's still a triangle. So the dilation didn't change the shape. So I'm going to say it's the same shape despite the dilation. All right, but okay, so we're addressing the angles, the shape is the same. What's the relationship between the side lengths? You probably know what it is, but it's not verified really. How do I know? Well, this really brings us to question 3. Here's what question 3 says. Label the vertices in the two triangles you created in the diagram above. Well, in our case below, right? Based on this diagram, write several proportionality statements you believe are true. First, write your proportionality statements using the names of the sides of the triangles in your ratios, and then verify that the proportions are true by replacing the side names with their measurements, measured to the nearest millimeter. Now, when I took my triangles out of my diagram, I lost their names, so let's put those back. So we had triangle A, B, C, triangle A prime, B prime, and C prime, and triangle A double prime, B double prime, and C double prime. Now I'm going to go ahead and give you some measurements that we already, I'm going to give you some measurements to save us a little bit of time. So this triangle has the side lengths of 40 millimeters. This side is about 31 millimeters. And this side over here is about 27 millimeters. And you can verify that using your ruler. Now I'm going to focus in on the larger triangle that we enlarged. So when I measured these side lengths, I got 120 millimeters for that long side right there. 81 millimeters here. And then over on this side, 93 millimeters. So I'm going to kind of summarize this question right here into something a little bit more concrete. Really this question, and this is what I think is a central question. The question is, in what ways can we find our scale factor, and that's our K value. Specifically, using proportions. Specifically using proportions. Okay. So I'm going to take this question and move that over here and say that that's kind of a summary of what this is asking. So if I was just looking at this small triangle and this large triangle, can you tell me a way that we could find our K value? So in this case, our scale factor was K equals 3. Is there a way to create a proportion to find 3 looking at these side lengths that we just outlined here? I'll give you a second to think about it, and then I'll reveal how we find that scale factor. So here's some proportions that I created to find a scale factor of 3. So first I looked at A prime C prime. That one is equal to 120 millimeters. And I made a ratio that compared it to its original measurement of AC of 40 millimeters. If I divide those, I would get 3/1. Same goes for all those sides. If I'm looking at the larger triangle, so B prime C prime has a measurement of 81 millimeters, and the original BC is 27 millimeters. If I divide that, I get 3/1. Last one. AB prime and AB. Let's check that one. AB is 93 millimeters, and A prime, B prime is 93 millimeters, and AB is 31. And again, that's exactly 3/1. Now the proportions we're really creating here that are worth noting are these. Those are all equivalent. A prime C prime over AC equals 3/1. Well, so does B prime C prime over BC. That also equals 3/1. And so does A prime B prime over AB. All three of these equal 3/1. So while the sides are not equivalent, they are all in the same ratio of 3/1. So the sides are all proportional. Which brings us back to what we noted here. So we said that the corresponding angles were congruent, that it was the same shape, but lastly what we're missing is this piece that the sides were all proportional. Sides are all proportional. In this case, they were all proportional to each other, equaling 3/1. And if you were to do the measurements of A double prime to C double prime, if you measured the smaller triangle, all those lengths, and you compared them to this triangle, you would find that they are also proportional. Now, depending on how much time you have, if you do, I would love for you to find those proportions comparing these two triangles that show that they can equal their scale factor of, in this case, 1/2. But if there is not enough time, then seeing this example is enough for me.